Okay, so I guess I'm not going to mess up again. This is my official version for the scrap paper and philosophy video 1. And what I'm going to try to do is use as much scrap paper as possible. So today we're doing hexadecimal numbers, and they're only printed on one side. So it's going to be good scrap paper. And let's begin by talking about the greatest book ever written in history, in the history of humanity, in the history of the planet, in the history of a species, the greatest book ever written. And you can get into a whole argument with Hindus about whether it's Genesis 1 or some section of the Bhagavad Gita. If I'm pronouncing that right, I don't know. But I think everybody can agree that this is the book. This is the book and nobody read it. So we did a little song and dance in the beginning to sort of acknowledge our shame for not having read the Latin version, at least. We haven't, I suppose. And well, if you're a Portuguese speaker, the title actually translates pretty nicely. It goes from Philosophiae Naturalis Principia Mathematica, and I know I'm not saying that right, to Philosophia Natural a Principio da Matemática. Now, if you're an English speaker, you can still give yourself a silver medal because the words for the translation are still pretty similar: mathematical principles of natural philosophy. So you see, the word order is different, so you only get a silver medal. But we haven't read the book. Okay, shame on us. But let's, speak a little bit about the history of science as an ersatz. And we have the 1600s. Newton was very much born in the 1600s. Although he may not be a creature of the 1600s, he was not aware of modern chemistry. I think that the periodic table is from the 1800s. Not sure, but I'm pretty sure that the major discoveries in chemistry that made the discovery of the elements possible happened in the 1700s. The gas laws, pressure, volume equals I don't know what, and the Avogadro number, stoichiometry, a lot of stoichiometry, I guess, came from the 1700s, and Newton wasn't alive to see it. So in Newton's world, there was earth, the four elements, right? Earth, fire, water, and air, maybe wind. And you can see, of course, the advantage of Newton's elements, which are going to be very different, of course. They're going to be... and here's my guess. I mean, if I was to hazard a guess of what are Newton's four choice for replacing the four elements, earth, fire, water, and air, there's distance, time, matter, which is just mass, another name. I'm just using mass and matter interchangeably, and energy. So here's four quantities or four elements. But of course, Newton's natural philosophy has a major advantage because it's going to relate, these four quantities with the formula force equals mass times acceleration. And I'm going to have to use scrap paper on explaining why force equals mass times acceleration relates these four quantities: distance, time, mass, and energy. So Uh, well, actually, I already did this. So we begin with force equals mass times acceleration. Okay. Now, um, remember that um, the units for energy is the Newton meter. Actually, this is a horrible way of doing it. So let's start with this. Okay. So force equals mass times acceleration, except we're replacing force by energy over distance. And why can we do that? Well, it comes from the definition of mechanical energy. Um, energy equals um, distance and times a force. Okay. So you're using a force through a distance, and that's our mechanical definition for energy. Now, the units of energy, okay, are in fact the Newton meter. Any energy you have. I mean, in the SI system, we're using Newton meters. Newton, remember, is the unit for force, and meter is the unit for well, meter is the unit for distance, and Newton's is the unit for force. Okay, so these equal the units for energy. Now, if we divide both sides by meters, we get this cancellation, and so we get that what's left is the Newton, which is a unit for force. Now, more intuitively, okay, let's do this more intuitively. We have this ratio: energy equals force over distance, and the question is why? Well, um, actually, yeah, energy equals force over that looks wrong. I think that looks wrong. Force equals um, energy over distance. And the question is why, intuitively? Well, if you're going to use a very large amount of energy over a very large distance, you're going to have an average sort of force. If you're going to use a very large amount of energy over a very short distance, you're going to get a very large force. Now, just think about it. It makes perfect sense. So once we got that, we have that this force equals mass times acceleration, except acceleration is a velocity. Remember, velocity is a distance, is a change in distance over a change in time. And an acceleration is a velocity changing over time. So it's distance per time per time. And when we add that up, we get that energy over distance equals mass times distance over time squared. If we multiply both sides by distance, which I'm just calling d, I shouldn't. And this is going to become a d squared, right? So we're going to get energy which I'm just going to call E. Energy equals mass times d squared over t squared. And from that, distance over time is a velocity. So we're actually getting E equals mv squared. I mean, how cool is that? It was cool enough for me that I wrote it down in this dead disk, this non-functional disk. I mean, I thought it was way cool, and we'll have a lot more to talk about this. But let's see. To make a long story short, I'm trying to do short videos, so I'm gonna upload this, see how well it works, and if I can watch it, if it's watchable, I'll continue. Thanks. Bye. See you soon.